Okay, in a previous video I looked at this titration and I saw what was going on before the equivalence point. I'm titrating the weak acid, acetic acid, with the strong base, sodium hydroxide. Now what I'm going to do is I'm going to go ahead and look at what's going on at the equivalence point. And what's going to be interesting here is, unlike with a strong acid and a strong base where the equivalence point occurs at a pH of 7, what we're going to see here is the presence of a weak acid is going to make this equivalence point occur at a different pH. So first of all, let's consider the acid-base reaction, and because it's at its equivalence, we know that the number of moles of each species will be equal. That's what we mean by equivalence point. CH3, COOH, reacting with NaOH to produce H2O and Na+, and CH3, COO-. Now, again, with acid-base reactions, whether they're strong or weak, if it's an actual acid and an actual base, we don't worry about any sort of equilibrium. These reactions are heavily favored and they happen to completion. So, here I have 0.2 molar of this, and my concentration, my volume will be 0.02 liters. Excuse me, converting 20 milliliters into liters. Here I have 0.1 molar concentration, and to get to the equivalence point, since my concentration is half as much, I need twice the volume at 0.04 liters. This is going to C equals N over V, so N equals CV. So this is going to get us C times V in both situations to a molar amount of 0.004 moles. Because they're equivalent, that's what we mean equivalence point, they're going to react completely, leaving none of the original acid and base behind, but creating these ions. And unlike with a strong acid and a strong base, the anion CH3COO- can still behave as an acid. There's actually 0.004 of all of these, but the only one I care about is this one, because this is the one that's the conjugate of a weak acid, so it itself can act as a weak base. So now we can set up that equilibrium. CH3, COO plus H2O. It's going to react to produce OH minus and CH3, COOH. That's an H. So that's the conjugate process of the Ka of 1.8 times 10 to the negative 5, I mean. So I can use my equation that relates direct processes to conjugate processes, where the Ka times the Kb is equal to the Kw. And here, assuming we're working somewhere around room temperature, we're going to assume the Kw is right around 1 times 10 to the negative 14. So 1.8 times 10 to the negative 5. Kb of the reverse process is equal to 1 times 10 to the negative 14. And we can solve for the K for this conjugate process. Exponent negative 14 divided by 1.8, exponent negative 5, and I got 5.5 times 10 to the negative 10. Okay, so now I need my concentrations here. I have my K, and before I can do that, I need to be a little bit careful here, because this is a number of moles, and I need to remember to find my concentration, because that's what I work in when I do equilibrium problems. So I've got 0.004 divided by my volume, and now I need to be careful here too, because I have this total volume. My volume is going to be equal to 0.02 liters plus 0.04 liters for a total of 0.06 liters. So with all that in hand, I can get a concentration of 0.0667 molarity. So that's my initial concentration. This is acetic acid that I'm dealing with right here. So, or not acetic acid, but the acetate ion, sorry. So that's my initial concentration of my acetate ion. I'm going to assume I have none of this, and because that was at equivalence, all of this is used up, so it's easy to predict the direction of my equilibrium shift. And so at equilibrium, 0.0667 minus x, and x. And so I can use my k expression, kb, is equal to OH minus CH3 COOH and CH3COO minus. Also, I can use my 100 rule. The concentration of my reactant over my K value is going to be 0.0667 over 5.56 times 10 to the negative 10. So this is going to be much greater than 100. So what that means then is that this change is small, and so 0.0667 minus x is approximately equal to 0.0667. Okay, now I'm ready to insert all my numbers into my K expression and come up with my concentration of hydroxide. 5.56 times 10 to the negative 10, x, and 0.0667 is the initial concentration of acetate. So doing this, I get an x value of 6 times 10 to the negative 6. Not 16, just 6. And I can recognize that that's equal to my concentration of hydroxide. My pOH then would be equal to the negative log of the concentration of hydroxide, which would be 5.2. And so my pH plus pOH is equal to 14, as I've shown in a previous video. So my pH in this situation would be 14 minus 5.2, or 8.8. So that's interesting. At equivalence, when the number of moles of both products are used up completely, what I can see is that I still have my anion associated with my weak acid. That anion, because it's a weak acid, the equilibrium process or the reverse process is possible. So it itself can act like a base. And so even though I'm at equivalence, I do not get a pH of 7, but instead I get a pH that's slightly different. This is very interesting because what that means then is that the equivalence point of this process, where remember our pH would be coming up earlier and then swing through, at equivalence would be something like 8.2. We can find different indicators that change color at different pH values so that our indicator can more accurately reflect where the equivalence point is, depending on where the equivalence point is in the titration that we're completing. We'll discuss that more when I do the video on the titration of the amphiprotic substance. In the meantime, I think, again, this has been long enough, so I'm going to do a quick video after equivalence point to show what happens if we have more of the strong base than the weak acid, and this is going to be a relatively straightforward calculation. So that is how you find the pH at equivalence when one of your species in your titration is weak instead of strong.